Good afternoon. Welcome to this lecture in the basics of macromolecular crystallography. We are going to show this lecture on Zoom every Monday at 1600 Berlin time. The lecture will cover really the basics of macromolecular crystallography and is mainly thought for students who either want to actively do these things, practice macromolecular crystallography in the future, or who want to know how it is done. So it will not only cover theoretical grounds, but also practical advice as well. If you have questions, you can write them into the chat window. You can also send us an email after the lecture or ask in the end of the lecture. You can also request to be unmuted if you want to interrupt me because you have a particularly urgent question pertaining to the current slide. If you have friends or colleagues who would like to register, please ask them to send an email to either lecture@thornlab.de or insidecorona@university-würzburg.de so that we know who they are and what their emails are. And then let's start. The first lecture is about crystallization. And I'll start with some numbers. So according to the National Institutes of Health, the total average cost of a protein structure in 2006 was assumed to be $1 million US. So if we assume that the winning crystal was 0.33 millimeters edge length, and that it consumed about 50% of the available funds, so it would have cost $500,000. We arrive at a value of $500,000 for a cubic millimeter, or 1.2 micrograms of protein crystal. If we take the 2006 high wholesale value for a flawless 5-carat diamond of 50,000, with 1 carat equaling 200 milligram, thus $50 per milligram of a top quality diamond, a protein crystal is about 12,000 times or 4 orders of magnitude more expensive than a quality diamond. I would encourage you not to think about this when you're mounting your crystals. Losing your protein crystal during harvesting is a very good example of a very expensive late-stage process failure. But today we are first going to talk about how we can get those crystals. And that is really the bottleneck of all of crystallization. I'm quickly showing you the experiment. We'll talk more about this in later lectures. So you can see here an X-ray experiment. The X-rays are emitted through a slit system onto the crystal, which is the cubic thing in the middle. And then the X-ray is diffracted by the crystal, which works as a grating and gives us spots. And from these spots, we can then calculate the structure of the molecules that make up the crystal. Of course, this requires a crystal. How do we get it? I'm going to talk about the theory of crystallization, mainly the phase diagram and nucleation, and also why you want a cat. Practical crystallization. So what are the different methods that we are commonly using? What do you need to look out for? What are the factors? All the little turns and knobs that you can tune to get a crystal: pH, temperature, precipitant, additives, protein modification, cryoprotection, and then things to consider. So tips and tricks, how to optimize your crystallization, getting ligands into your crystal, and a little bit extra about membrane proteins. I'm going to finish with a summary. In theory, what is a crystal? So this definition is a little bit of an older definition. It is a solid material whose constituents are arranged in a highly ordered lattice that extends in all directions. We used to say it's translationally symmetric, and that is still true. So it's made of the same ordered molecule in 3 dimensions. That makes a 3-dimensional crystal. However, real crystals are not perfect, they're also finite, and they consist of multiple slightly misaligned domains. Bernhard Rupp, from whom the quote is that I just told you about the NIH and the 1 million US dollars, also made this picture, which kind of shows you this concept of mosaicity. So, because proteins are flexible and wobbly and the interactions are rather weak, crystals really are not perfect, and protein crystals are messy. There are periodic self-assemblies, and as I just said, the proteins are large, flexible molecules held together by weak intermolecular interaction. So protein crystals are actually quite soft. Most of them are approximately as soft as butter, which makes our life quite difficult when we try to move them, for example, on a slide, because you have an acupuncture needle or a tool and you try to shift your crystal, but it's sticking to the glass slide on which you crystallized it, and then it can break, or you can just smush it. So it looks still somewhat fine, but when you put it on a diffractometer, it doesn't diffract because its order was sustained by such weak force that, well, it was just squished. Many trials are necessary to obtain suitable crystals because crystallization is an unlikely event for such molecules, and you also need an extremely pure protein to start with. So this really is a major difference that we explain to people who come from small molecule crystallography, where crystallization can be a method of purification. In protein crystallography, we really need to start with something that is already rather pure. So here's a video that shows crystal growth from the Elias lab at the University of Minnesota. These are 8 hours, and the drop is approximately 2 millimeters in diameter. And you can see that crystals are forming. You can also see a little bit of precipitate in the middle that was there from the very beginning. And here you go, some crystals have formed. Now, whether these crystals are good or not remains to be seen. Crystals like this, while for a small molecule crystallographer or chemist look terrible and they would throw them away immediately because they have no regular shape, you can see that the edges are rather rugged. As a protein crystallographer, I'm not that strict. My crystals can be ugly and sometimes they diffract nonetheless. So I'll just slap them on the diffractometer, and if they diffract, I'm happy. So what brings on crystallization? A protein solution must become supersaturated and metastable in order for crystallization to happen. Phase separation must occur by means of, well, nucleation, solid precipitation from the solution. Liquid phase separation also can start. This looks then like having oil and water mixed. So you have 2 phases, but both are liquid. And crystals may form while the solution equilibrates. Now, how does this look in a phase diagram? Imagine you have the protein concentration on the y-axis and the precipitant concentration, that would be, for example, a salt, on the x-axis. Now, at this point, you have pure water, no protein and no precipitant, and their concentration increases if you go to the right for precipitant and up for the protein. Here, this line is called the solubility line. Now, this region is metastable, and here the crystal is unstable, so there's instability, decomposition, 2 phases, or precipitate. In the metastable region, phase separation is possible in a protein-rich and a precipitant-rich phase, and also crystals can form. And here in the blue region, you would have a clear protein solution, a single phase, and a stable form, everything being liquid and homogeneous. Now, crystallization is an entropy-driven process, meaning that water molecules are released from solubilized protein. So if you try to remember what entropy is, it's basically more messy, a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as the degree of disorder or randomness in the system. This is the dictionary definition. What does that mean? So the protein is in solution and it is surrounded by ordered water molecules that bind weakly to its surface. So there is an entropy gain of the solvent if it leaves the protein surface as the protein crystallizes, and that entropy gain exceeds the protein's loss of motional freedom. When I was a student myself, this confused me to no end. I did really not understand how an orderly crystal and its formation can be an entropy-driven process. And the secret is all in the water on the surface of the protein. So the water gets free, and that's where all the entropy comes from. Crystallization must be both kinetically and thermodynamically favorable in order to occur. So can you think of kinetic factors for crystallization? There are, for example, gravity. In the old days, people wondered whether it would be possible to grow crystals in space, and they actually tried. Nucleation rates, growth kinetics, so how do the molecules bump into each other in order to form the lattice? What are the microscopic foundations? These are all questions you should ask yourself, not only in theory, but also in practice. When you look at your construct and the kind of like crystallization environment you put it in, these have all implications. For example, the movement in a solution is much higher at a higher temperature, and it becomes lower if you add, for example, polyethylene glycol, because the whole thing becomes more viscous. So it plays a role. How does now the crystal form? So this is the same phase diagram as before. And now let's start. So we put a drop with protein and some salt, and that drop slowly evaporates. So the precipitant and protein concentration go up. We come out of everything is a clear solution stage into the metastable phase. And here we reach a point where spontaneous nucleation can occur and a crystal may form. At this point, the protein may start to precipitate or form a crystal, in which case the protein concentration will drop and the precipitant concentration keeps dropping as the drop slowly evaporates. So it also drops a little bit, which is why the second arrow is not pointing directly downwards. This happens as long until the solution border is reached again, and then it goes back. So at this point, the growth of the protein crystal mostly stops. The thing may even like dissolve a little, and the growth will either grind to a halt or become very, very slow, and more evaporation from the drop has to happen for it to be spurred into action again, at which point in time the crystal grows. Of course, the process in reality bounces back and forth more than like 3 times during the whole crystallization process. It's a continuous process. Now, what you really don't want is by the moment that you mix the whole thing, for example, you're adding salt to your protein, to flop up into the decomposition or even homogeneous nucleation, which gives you like 1,000 mini crystals, each 1 micrometer and too small to measure. You really want to stay in the heterogeneous nucleation phase where everything is happening slowly and orderly. In this lower region of the metastable phase, crystals can grow, while here stuff may just precipitate. It does not necessarily, it can also form small crystals, but it's not what we want. What we want is something that plays out here. But at a low saturation, as long as you reach this border, you have no nucleation. Spontaneous nucleation only happens in the upper region. So at a high separation, nuclei can form easier. How can we induce it? Well, there are methods for this, and one of them is seeding. And this is why you need that cat. So there's macro seeding, in which you take a crystal that you've already made of the same substance, sometimes a different substance, but in protein crystallography, it's typically the same protein that you have crystallized earlier, but the crystals were, for example, not perfect. You take, or too small, you take those small crystals into a new solution that has equilibrated, and that hopefully is in that lower metastable region, and then the crystals will grow larger. This is called macroseeding. Microseeding is when you introduce nucleation that is so small that you can't even see it. And we typically do this, for example, by streak seeding, for which we prefer to use cat whiskers. So you take a cat whisker, you clean it with acetone, you glue it into the tip of into a pipet tip with, like, you know, epoxy glue, whatever you have at home. You glue it in there, you take your cat's whisker, you brush your existing crystal, you wash it off with millipore water, and you whisk it through several conditions while washing it in between. And what you can see here is exactly the line along which the hair went through the crystallization drop. And along it were many little nuclei that all formed their own crystals. And as you can see, there's a very high concentration of nuclei was here, so this is not usable, but later in the drop there was a lower amount of nuclei, only one or two, and single crystals have formed. Here you can also see an example of the speed of crystallization, which is also important. So these are different trials. In this one, there were too many nuclei to start with in the seeding, so we only got some very small crystals. These ones are a little bit better, but of course, if you could choose, you would like those very large, nice crystals. So practical crystallization, how does it look in reality? By the way, all the images in this are from 5-beta progesterone reductase, which once crystallization conditions were established, grew pretty fast, but it had its own problems, as you can see on this image, where you can see that it crystallized so fast that there were no single crystals. Everything was grown into each other. So what do we want? We want a single crystal. We don't want multiple crystals intergrown, preferably with a blocky regular shape. We don't like to have plates or needles. Ideal is something blocky that can be handled. A correct size for your experiment, it depends what you're measuring at, but typical edge length is about 100 micrometer or 0.1 millimeters. You want good, strong diffraction, single mosaicity, meaning that your crystal should be as regular as you can possibly have. You don't want ice rings, so you have possibly to use a cryoprotectant if you are measuring at cryogenic temperatures, which is almost every measurement today. You don't want cracks from fishing the thing. And you would also like the correct protein structure. Now, this may come as a surprise to you if you've not been for a while in a lab. But every here and then, I get sent problem structures from people who can't solve their protein structure, for example, by experimental phasing. And they write to me, "Dear Andrea, we have this crystal that we got after 4 years in the lab, and we can't phase it for the love of God, although we are sure that our heavy metal is in." And then you calculate it through and you find out that there would be 0.5 monomers of their sequence that would actually fit into the volume of the asymmetric unit. So from the measurement, you know how large the unit cell of the crystal is, and you kind of figure out that the protein doesn't fit into there. Then you check the unit cell against the PDV, and you find out that, well, it looks like, for example, lysozyme. And then you put in a molecular replacement with lysozyme, and ta-da, they have purified for 3 months. And what they got was lysozyme. This happens all the time because there are so little checks that you can make. You can make Western blots and so on, but you need an initial suspicion that something is wrong. And mostly these people are really happy if some lyses. You also can get salt crystals, but you recognize them usually already in the diffraction stage. So this is a comic that I found online from the Siemens lab, and it explains how crystallization protocols work, how crystallization works. You guess the conditions, you set up the crystals, you pray for crystals, look for crystals, you guess new conditions, you set up crystals, you pray for crystals, you look for crystals, you change DTs, which means you've changed your strategy. And as you can see, there's nothing in this picture that says found crystals. And this is typically the first 2 to 3 years of any PhD thesis in macromolecular crystallography, where bouts of like cell culture optimization, purification, and crystallization follow each other in a seemingly endless pit of despair. Because crystallization, just as it happens, is the single most difficult challenge in a crystallographic experiment. And it is a pretty unpredictable one too. So crystallization conditions cannot be predicted ab initio. We cannot look at your sequence and tell you, well, please use 20% PEG and tris buffer at pH so-and-so, it will crystallize. This is not possible. The whole thing is more like alchemy. Not only do you use cat whiskers, there are a number of other rather obscure ingredients which we are using in just the hope or praying to our deity that the stuff will crystallize. The search space for screening is of course large. You can change the temperature, the pH, every chemical that you add, its concentration, the method of crystallization. You've got seemingly endless possibilities. It is also a very ill-defined search space because you don't know, should I stop at pH 4 or should I go to 3? And it can only be sampled sparsely because you and no one else wants to set up 10,000 different drops. People do this from time to time, but you will later see it's pretty unwise given the statistics. Efficiency should always be considered when doing crystallization. Wishful thinking is really not good here. You need to be efficient. And that sometimes means you have to go back and change your construct. You also should be very crystallization tips that lack rationale. So if you don't understand why you should use a dog whisker or a cat whisker or PEG 400 instead of PEG 800, but postdoc said so, ask why. There's a lot of like superstitions around crystallization, and a proper design of experiments is needed. And you also may want to read up. If you've got really no idea, try this one, McPherson, Introduction to Protein Crystallization is an excellent starting point, along with the book from Bernhard Rupp, Biomolecular Crystallography. So say you've purified your protein, I would recommend a gel filtration column, even if you have a good his tag and you have done an affinity column, put a polishing column in the end. Use the protein as fresh as you can get it. In particular, if you don't know whether it tends to decompose, don't freeze it. Use it after gel filtration to pipet out your first crystallization trial. In an average lab, the first trials will be robot or manually pipetted sitting or hanging drop plates, which are sitting drop plates are depicted here. I'm going to explain this, I think, on the next slide. These are sitting drop plates. That means that the protein goes in the middle and the well is around it. Sitting and hanging drop are vapor diffusion methods. And you want to start with a pH PEG screen or an index screen. These are screens that sparsely cover quite a range of possible conditions. And where differences between protein batches can be fatal. So you do a purification, and if you don't do the next purification exactly like the first, you may get different results. So reproducibility and a good documentation are also necessary for your purification. Sitting and hanging drop methods reach supersaturation by vapor diffusion. That means that the protein is sitting up here in a drop. This drop is usually a cover slide, circular cover slide. A tight seal is achieved by grease over a closed well. So the whole thing is a closed system. On the bottom, you have a salt solution. On the top, you have your protein often mixed with some of that salt solution. And now what happens? The amount of dissolved molecules or ions in the bottom well is higher than in the drop. So there is a tendency of water to go into the space between the two and to accumulate in the well, because the system wants to equilibrate. It wants to have the same amount of dissolved particles, dissolved molecules or ions in the drop and in the well. So there's more evaporation happening where the water goes down into the well than evaporation of water is happening where the water ends up in the drop. And so over the course of several days and weeks, the drop becomes drier and drier and drier. But the protein is so huge, it cannot evaporate. So it will remain there. And so will most of the salt, because it's also much harder to evaporate salt than water. As this happens, the protein may get into the metastable region and start to precipitate or form crystals. Sitting drop uses the very same concept, only that the drop is not hanging. It is sitting in a well that is suspended above. So you can see this here, but the concept is exactly the same. And not only does the protein concentration in the drop increase, also the precipitants. Has anyone an idea to what that could lead? That can lead to a very common problem. You get not protein crystals. Your protein decides to precipitate or not do anything, but you get salt crystals. And you're very happy because you, after 2 days, have this beautiful, nicely shaped, blocky crystals. I really recommend using a polarization filter at this point in time before you open the condition. You will quickly find out that it's salt because it doesn't polarize light, at least if it's a normal salt and not an enantiomeric one. And you can just leave the plate because the salt may form crystals, but so may your protein. The next one is microbatch. In microbatch, you only have one solution of your protein with the precipitant and salt and whatever, which is covered under oil. So on the bottom, you have this microbatch sitting there, here. Actually, that picture is microdialysis. I'm very sorry. But the plate is correct. So you have down here, in the wells, you have your drop and it's covered in oil. So you basically cover the entire plate in oil. Yeah, you pipe it in each of those holes, you pipe it some oil. It can be silicon oil that is a little bit like, that can be pipetted, or paraffin or else oil, whatever you like. You pipe it in each of those wells. And then you pipette your protein solution already readily mixed on top of it, and the drop sinks to the bottom and is then covered by the oil. Evaporation happens here slowly because the oil keeps stuff from evaporating. What is very nice about this method is you need very little material. You don't need to seal. There is no rush. It's not like a 96 sitting drop plate which needs to be like glued shut as quickly as you can, because under the oil nothing happens anymore. So you have all the time in the world to pipette that thing. And I think it's an underestimated method. Now, here's microdialysis. In microdialysis, we have a button in which we bring the protein solution. Then it is covered by a dialysis film, which will let water go in and out, but not protein. And then there happens a solvent exchange, which will concentrate the protein and hence also lead to concentration. This is a particularly nice method to get really large crystals that are usually really, really beautiful. So it's a good method if you've got something that crystallizes, but it never forms very nice crystals. It's also good for volatile compounds because it all happens in a microdialysis bath. So, for low ionic strength compounds. The last one is free interface diffusion. In free interface diffusion, I couldn't find a very nice image. You have usually a microfluidics device, and you have the protein and a precipitant. So you've got a protein that would like to crystallize but is stable, and you've got something that will make it precipitate. And you have an isolation valve which you release, and then through the powers of diffusion, the two mix. And where they mix, crystals can form. This method is also used in small molecular crystallography, typically with a solvent in which the compound is more and less soluble. Here, you cover the entire phase space in the microfluidics device, which is very nice. So you don't need to worry too much about where's my metastable region, because actually you can use quite a lot of precipitant and then it will just crystallize a little bit more in this picture to the left. And again, you need very little sample. The downside is you need a specific device for doing this and often rather expensive kits, while those microdialysis buttons that I'm showing above are both cheap and very reusable. Protein properties need, of course, the protein needs to be pure. Denaturation is problematic. Check by SDS gel. If you've got the feeling that your protein is just decomposing as you look at it in its ice bath, it's not going to crystallize. Spin it down before dispensing. If anything precipitated prior to crystallization attempt, you don't want it to go into the drop. It could, be a problem for your crystallization. So gently spin the stuff down before you set up your crystallization plates. You have conformational homogeneity. This is something that you want. You want stuff that is not too floppy, but you can't do very much about it. It may be conformational heterogeneous. If so, you may want to lower this. And concentration is a very important factor. On average, your best chances are 14 milligram per milliliter. As a rule of thumb, there are, of course, exceptions. Often, the higher, the better. If the protein is still stable at like 30 milligrams per milliliter, well, you may want to use that and try it. You know that you have a good concentration when you can make the stuff precipitate on purpose. And in order to do this, you make one drop with 30% PEG per 1000 formula ammonium sulfate and 30% isopropanol. If it does not precipitate with this, you need to increase concentration further because, well, it should fall out. Also, if you do your first screen of, say, 100 index conditions, and you find that about 1/3 to half of the conditions contain precipitant or some kind of like stuff, that is a very good sign. It means your protein concentration was right. If you dispense 100 well plate and none of the things shows any precipitation whatsoever, your protein concentration was too low and that stuff will never crystallize. And the stock should be a mild organic buffer such as heat piece and as few reagents as you can manage. Why mild? Well, you want the precipitant that you add to dominate pH. You don't want, the buffer in which the protein was dispensed to dominate the conditions. And calcium ions and phosphate can be bad, but not necessarily so, and should be avoided if you can. Now, what's the role of pH? The actual pH in a crystallization drop is rarely known. Many things crystallize around physiological pH 7.4 for not quite clear reasons. The stuff usually doesn't like to crystallize at the isoelectric point. So this might be because at pI, the protein may be very susceptible to small changes in pH or have fewer electrostatic interactions. Acidic proteins tend to crystallize well 1 or 2 units above pI, basic proteins 1 or 2 units below their pI. So this is just a rule of thumb, but helps you to plan out an initial strategy. Typical screens will also cover a number of different pH values, but if you've got a particularly acidic or basic protein, you can possibly do away with a few of those. In particular, if you're hard-pressed for protein, if you don't have enough protein and you can only do a sparse screen. Typical temperatures to crystallize are, for obvious reasons, room temperature, 4 degrees. If it would be possible to crystallize many proteins at -20 and -80, we would also do so, because that just happens to be what our labs can provide. Low temperature affects kinetics, right? Kinetics are faster at high temperature and slower at lower. So sometimes lower is better. And if you have a very high ionic strength, the solubility of the protein decreases with the temperature and vice versa. You want to keep that in mind. So if your protein did precipitate in all your conditions, you may not want to warm the plate up. You want to do the next one at a colder temperature. It can have an influence on twinning, but this hasn't been established by a study yet. It's just gut feeling, having seen quite a few twinning structures, that it may have an effect. Then there's the precipitant. That's what should make your protein crystallize. It stabilizes the protein and mediates crystal contacts during formation and also after formation of the crystal. Fine-tuning of molecular interactions may be necessary. This is why we choose from so many different precipitants. And there's also an effect called salting in and salting out. So here you can see a curve of solubility versus salt concentration. And what you can see is that the solubility is rather low at low salt concentration, then increases and then decreases again. And this is thought because the protein likes to stick together if there's not much salt. The protein likes it if there's a little bit of salt and it can satisfy all the possibilities for ionic exchanges on the surface, like a lot of interactions. But if there's too much salt, the protein likes to stick together again. This is basically salting in and salting out. So you start in the middle and you either lower the salt content in order to make the crystal form nuclei, or you increase it. Most people will increase it. Well, many precipitants are salt. I so far only talked about them, but there's also PEGs. So PEG and PEG monomethyl ether, they compete for the water molecules in the hydration shell of the protein. They decrease, hence, the solubility. They make the whole blob highly viscous. You're going to see that in a video later. Also, bacteria like to eat them. I cannot repeat this enough. Bacteria like to eat them. Mold also does. So, bacteria will settle in your crystallization plate. Better wear gloves when you dispense that stuff. And You can put some stuff in to at least stop mold from growing and bacteria. Also, batches of PEG can be different because PEG 400 just means that, well, it evens out at about a molecular weight of 400, but around that, it hopefully is Gaussian distributed, but the reality is that every PEG batch is different. So there were a few famous PEG bottles in the lab where I did my master's. There was in particular one PEG bottle which was very much cherished by our main crystallization person of a certain batch of I think PEG 2000 that had been made by Hampton. And if she really could not get something to crystallize, she would use that magic bottle. And while, well, you may speculate whether that's a real thing, I can tell you that different bottles of PEG are different. And it's better to stick to your favorite bottle of PEG. If your lab allows for it, you can, you know, make a little heart or a name sign or a little like skulls and crossbones on it, so you know this is the bottle of PEG that you use, or just write in your lab journal the manufacturer and charge number. Additives. This is the speculative category. Here you can add anything. It's often used in optimization steps. Some examples include divalent cations, which promote in intermolecular contacts because they can interact with like two charged groups. Mild detergents, so they can change the protein aggregation state, resolubilization from inclusion bodies, for example, from E. coli, and membrane proteins. Small alcohols, DMSO, organic solvents, decrease of dipole moments. Proteins are more attracted to each other. Beta-mercaptoethanol prevents oxidization of cysteines, so it can help with your sulfur bridges. There's a lot of different additives out there. There are even some which can protect your protein a little bit from radiation damage. Then, last but not least, nothing has worked. You've changed the precipitant, pH, temperature, and additive. You've changed your method of crystallization, so you can't do anything. You want to modify your protein. You can do targeted design, looking at the sequence, looking at secondary structure prediction, and decide that you need to get really rid of that C-terminal end. Do a targeted mutagenesis. You can also introduce some more interacting groups. You can do random mutagenesis and library screening. You can truncate domains. Say you've got two domains, you can truncate one off and crystallize only the one you're interested in. You can use fusion proteins and tags. My personal opinion is that tags are not detrimental to crystallization. However, again, this is only gut feeling. There is no systematic study of this. If your protein happens to come from cells which glycosylate, and there's a lot of glycosylation, you may want to get rid of that glycosylation, because glycosylation in nature is making stuff slimy on the outside. That's its job, making stuff slimy. And if you want to make a brick wall out of slimy stuff, it's not going to work. Phosphorylation and dephosphorylation may play a role. You can do limited proteolysis. So during my PhD, I had a protein which would not crystallize for 2 years. It had been successfully deglycosylated, or so we think, but it never would grow. However, I had several plates in which there was mold. And after 5 months, in one of these moldy plates, where I could see beautiful mold, like black strands of mold in my drops, there were crystals. And they diffracted to 1.6 angstrom. We could never do it again. We only had that one drop and the 3 crystals that were in there. And we think that mold may have eaten either rests of glycosylation or the protein. That's not exactly what most people use in the lab for limited proteolysis. You possibly want to use a kit, you know, from a major company. But so it can happen. And of course, cross-linking. You can basically throw stuff at your protein that cross-links it, that makes it very, very stable. However, it may then not accommodate crystallization packing. You can, by the way, also cross-link your crystals after you made a crystal out of them. And this is also very popular, of course, in cryo-EM, where they cross-link all the time. Cryoprotection, well, most measurements happen at cryogenic temperatures. Crystals may need cryoprotection in order for water not to form in the crystal. I'm going later to show how much water there is in a crystal. Let me say there's enough water in a crystal that if it would be crystallizing, the crystal would just get cracks and die. So you need to protect that water from crystallizing as you cool the crystal. It's also very wrong to say you're freezing your crystal. You're not freezing your crystals in liquid nitrogen. You're cooling your crystals. You really, really don't want them to freeze. Don't say that. Some crystals cannot be successfully cryo-cooled and must be measured at room temperature. If your crystal doesn't diffract, one of the first questions I always ask is, did you try if it diffracted at room temperature? Because both cryoprotection as well as cooling the crystal can lead to deterioration. And it is good to establish that the crystal diffracted at least at one point in time. There are different things to choose from. Glycerol is very popular, so are PEGs, which are often already in the mother liquor, so they're there. I had some good experiences with glycosylated proteins with sugars. There are also salts. And I'm not listing this here because it's a little bit exotic, but you can also dump your crystals in oil. Here's a picture from Sabrina Stebb's bachelor thesis in my group. What you can see is perfectly neat looking cytochrome C crystals, which she got after a lot of work. And then she added her cryoprotectant. And this picture was taken approximately 2 seconds after she added that first little bit of cryoprotectant. And that was the crystal after 2 seconds. What you also can see is that the salt in the crystallization drop, now that the drop is open, rapidly is forming crystals as well. So that we had a lot of data sets from these crystals in the crystallization solution that were not protein, and no good cytochrome C data set, or none that was really perfect. She eventually optimized cryo conditions. And in this case, we didn't want to do room temperature measurement, but it may have been indicated here. Last in the practical section is how to fish the crystal. This is the step at the end where you are taking something that tiny with your shaking hand into a loop. Gianluca is eventually going to tell you more about this in 2 weeks' time, but you really want to choose a loop that has the right size and flexibility, and you want to practice this with some lysozyme crystals or so before you do it on something expensive. Because you have to be quick, and you only get to be quick by doing this a lot. So here is the video. There is the loop. It's a sitting drop plate. You can see the whole thing is very viscous. She tries, she doesn't catch it. And there we go, it's sticking. You can see it's sticking. She takes it out. She will now very quickly drop it into liquid nitrogen. It must have already been cryoprotected before she fished it. Or she has to take it out and put it in a cryoprotection. I'm going to show this again because this is really like a beautiful, beautiful example of how to do such a thing. In particular, given that the drop is relatively deep and it's clearly difficult to see how deep you're in or how deep the crystals are in there. Flop, and it's on. The loop is just a little bit smaller than the crystal, really perfect, not too much mother lacquer on it. I would possibly wick it, but that's how you do it. Things to consider. By the way, here another beautiful picture of what can happen to your crystal. Perfectly nice crystal, unfortunately sticking to a thick viscous membrane of precipitated protein. Very difficult to tear open, very difficult to get away with. If you leave it on the crystal, you have half the drop hanging on there, so you can't afford this. You need to get rid of it without damaging the crystal. Optimization. After your initial screening, you found some crystallization conditions that you like. you need to optimize around those conditions. So you will then take that condition that you have and kind of like screen a little bit more closely around it, change pH just a little bit, change precipitant concentration a little bit, possibly try a different crystallization method if you don't like the look of the crystals. Salt, single, and twin crystals can be distinguished by using a polarization filter for your microscope. So this is a picture from heliothionine D from Helleborus progressans. When my student Carlos Eduardo Tajunia showed me first these drops, I told him that this was his first plate and phase separation occurs very frequently. Of course, it wasn't colored, right? This is a polarization filter image that we took later. So we threw away the first plate, I believe, and then we did another one and we got this stuff again. And then I happened to just rub in there with an acupuncture needle and hit one of those blobs, and turned out they were solid. So we put a polarization filter on a microscope, and as you can see in the color difference, the stuff was protein. At least it was something enantiomeric that rotated the polarized light. So this were actually protein crystals that again diffracted to 1.8 angstrom resolution. Although they're not even like having nice edges. Goes to show ugly crystals still can give you beautiful data sets in protein crystallography. You can also again nicely see the precipitation on the base of the drop. And you can also see that this crystal here is not a single crystal. Can you see that? So what you usually do is you turn the polarization filter on the top of the microscope while you're looking through it, and you see if you can make the crystal go completely dark. If that is the case, and it has not two colors, but one, and it goes dark and bright evenly, it is a single crystal. Also keep in mind, single screen, no adjustment, 10 to 20% chance for diffracting protein crystals on first try. Large-scale trials have shown that if no promising results are obtained after 300 trials, it might be quite difficult. So you can stop after 1,000. You don't need more than 100 conditioned plates. You should then change construct or do some protein engineering or something. Proteins that crystallize in many different conditions may also diffract well. Affinity tags rarely hurt crystallization. Crystallization drops can be settled by mold, we already had that. Rapid growth may yield defects, so you want slow growth, not too slow. I mean, your PhD thesis has to end eventually, but if the stuff grows in 2 hours, the crystals won't diffract very well in most cases, unless it's lysozyme. Well solutions regulate kinetics and supersaturations, so you can add salt to the well solution if you think your drop needs to lose some more water. Crystallization cocktail is usually given as before mixing. So if there's a pH in that, that means stock solution pH, not pH in your well. This is very, 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 very important when you want to reproduce someone else's crystallization conditions, and it's not always said. Problems and tips. Drops clear. No supersaturation reached. Increased precipitant. Increased protein concentration. Insufficient nucleation. You may try seeding, vibration, or rubbing on the. If there's glass, rub on it with another thing of glass. Try to introduce, something that will help. Seeding is definitely the best here. But if your macroscopic seeds are dissolving immediately, you just have a problem with the precipitant and you need to add more. Crystals too small. Try macro seeding. So take the small crystals, put them into a new equilibrated solution so they don't dissolve right away. Use a special beamline for very small crystals. There are several of them around at ESRF and Diamond, for example. If it's a really important, and at Petra too, there are plenty of different beamlines now. If it's a really important project and you can produce masses of very small crystals, you can consider going to the X-well. Tips: take pictures of your crystals a lot. They not only do they look very nice in any publication, they also help you to document what has happened and to prove to your supervisor that yes, Your protein crystal was beautiful before it dissolved again. Plan your observations, do them on a regular interval, implement a scoring system if you must, but better yet, don't pipette so many plates. Learn to distinguish the ugly from the hopeless. This comes only with experience, but after, having put 40 of your hopeless crystals onto the diffractometer, you may get an inkling that that is like a lost cause. So are crystallized proteins still the same as they are in a living cell? Flexible regions may accommodate packing, but the core fold is mainly conserved, and enzymes, as has been shown, typically remain active in a crystal packing. So the conformational change is not as much as that the function is inhibited. And even in vivo, proteins work in very packed environments. On this picture, you can see an E. coli cell painting by David Goodsell. This is the E. coli. And then you can see this little bit here. That is this thing magnified. And the little blue dots are the water molecules. And this is the protein. And there's lots of other stuff around it. So it's really living in a packed environment. That's possibly why they still work when they're crystallized. If you are doing co-crystallization, that means you want to add a ligand. You very often do this for drug screening. It's currently, for example, done with the coronavirus proteins, where people are adding ligands before crystallization in the hope that the ligand binds to the protein and they can then get a structure of the ligand bound to the protein and prove that it's binding at a certain spot. It's very good when the compounds are insoluble. That you cannot make a good solution with high concentration. You can consider a warm incubation of the protein before you dispense it. You can consider adding the cryoprotectant early if your ligand is particularly hydrophobic. Solubilization with DMSO or other pharmaceutical carriers. There are, for example, big ring-like structures that are used to bring drugs into human bodies that are lipophilic. You can also use them for co-crystallization. They're also good. So co-crystallization is also good when the protein aggregates easily, so that you don't have, to soak it later. You can do this in the start. You can also consider doing a co-expression, which sometimes stabilizes the whole purification process. And if you get no crystals with ligand, but you get some crystals without, you can also consider cross-seeding with a non-ligand protein. So you grow your crystals without, you take a tiny crystal, do macro-seeding into the solution that contains the ligand, and hope it will grow and grow and grow and include the ligand, and there was just a nucleation problem. Now, this may come as a surprise to you, but your protein crystals are only about 55% ordered. The rest is an average disordered solvent. That is just looking different in every unit cell. It's mostly water. It's like a soup. There are organic molecules, salt, water, glycerol, whatever you put into your crystallization. And here's a picture of, again, heliothionine. And you can see, so these holes in the crystal lattice packing are approximately big enough that 3 proteins would fit in there. They're about 80 angstroms across. So these pores can be huge. And that's also the reason why our crystals are so squishy. However, these voids and channels allow us to soak small molecules and ions into the crystal. You should always think about diffusion times, right? If you want to soak in a 30 amino acid peptide, for like 5 seconds, that peptide will not bind to anything. But if you're soaking in iodide, that will go very quickly, which is why there is a method called iodide squishing, where you just squish your crystal. So soaking a crystal after it's grown. Aqueous solutions are ideal, of the ligand, of course. Optimize soaking time and ligand concentration. Soaking may take long for weak or large ligands, as I just said. The protein crystal can deteriorate. If that is the case, do a stepwise concentration increase. So just have drops and put the crystal through the drops, or add ligand solution mixed with buffer to the drop. Stabilization buffer for the protein can help. Also consider co-crystallization, which is generally, I would say, better if you can do it. Hydrophilic ligands, add them before you add the cryoprotectant. Hydrophobic ligands, add them after the cryoprotectant, because most cryoprotectants are pretty hydrophobic. I mean, speaking of cryoprotectants, right? They're not hydrophobic on a grand scale of things, but they're more hydrophobic than water. Consider also, again, co-crystallization. Now, false friends. You may have worked very hard to get your ligand. Many things go into binding sites. Many things like to bind to proteins. They are always never fully occupied. What you can see here is picture A, the presumed ligand. Picture B, TES buffer in the ligand binding site. Which one do you think fits the density better? But if you've worked for years to get that, which one would you more likely believe? This is a real problem. So scrutinizing your own ideas very harshly when it comes to ligand binding is a good idea, and also doing things like omit maps. You need to critically assess both the structure as well as your wishful thinking. Or as Nick Pierce put it, not sure if ligand or just 10 waters. Extra membrane proteins. That could be an entire lecture. I'm only going to quickly scrape it because they're an important class of drug receptors. Most drug targets are membrane proteins of one sort or another, and transmembrane parts are hydrophobic. So they don't like our aqueous crystallization conditions. Hence, they're difficult to crystallize and to concentrate and to purify. A protecting detergent color can help. So you add some detergent, and that detergent, as shown in this picture, forms very nice micelles around the protein. They even can do something which is called liquid cubic phase, which makes a whole scaffold around that makes the membrane protein orderly. In summary, plan your experiments, also your crystallization experiment. Good protein sample, pure, stable, good buffer is key. Typical starting points are index screens and sitting drop plates, typically pipetted by a robot in large labs and hand pipetted hanging drop plates in smaller labs. Control pH and temperature, choose a method. Your mother liquor is a buffer, precipitant, and additives as outlined. Your ligands, you can co-crystallize or soak in. You will need to optimize. Think about the composition of the drug, potential protein modifications that can help you, seeding, cryoprotection. Don't be afraid to go back 2 steps instead of 1. If you've already done 2,000 different conditions, another 1,000 are just not going to cut it. You need to change something in the purification. That was, well, the basics of crystallization. I hope this will prove helpful. This lecture was very practical. The next one will be a little bit of storytelling with the history of crystallography, and then we're going to dive deeper into the underlying theory of crystallography. And I am, well, open for your questions.